Okay, Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, today we'll continue talking about an introduction to deep learning, and especially the three types of machine learning that we talked about last time: supervised, unsupervised, and reinforcement learning. Before that, let me get a quick recap of what we have mentioned last time. So last time, at the end of the lecture, we talked about the relationship between AI and machine learning and deep learning, right? Can any of you remind me of what are these relationships? Yes. Yes, machine learning is a subfield of AI. Yes. Okay. And how is deep learning related to neural networks? Do you remember? Yeah, so the neural networks is the model itself that we build, the system that we will use. Sorry? Exactly. So this is how we, by deep learning, we mean how we fit that model to data, so that we get one model that hopefully will be good for our purpose. Okay. So we went through, I think, these questions together last time. I think towards the end of the lecture, AI is all about deep learning. No. What is fitting mathematical models to observe data? Machine learning and deep learning, because deep learning is a subfield. Deep learning is equal to machine learning? No, of course not. Any machine learning models is deep learning. And what is a type, whatever the sense of the type is, of machine learning? All of them. Okay, you remember. Okay, why is it all of them? First of all, deep neural networks, of course, is one of the models of machine learning. Supervised learning is an area within machine learning, and deep learning is an area of machine learning also, okay, or any subfield of machine learning. So all of them can be considered as types of machine learning, okay? And that, I think, was the last thing we did in the previous lecture. Any questions so far? Any question from last lecture? Okay, so let me start back now from where we stopped. So this is the picture that we had before, and these are the three types. So let me pointer. These are the three types of machine learning: supervised learning, unsupervised learning, and reinforcement learning. And we said that the state-of-the-art solutions in all of these three areas are now powered by deep learning. And that's why we will focus, inshallah, in this course on deep learning. So now let's give very brief introduction in this lecture on each of these three areas, okay, to see how they are different. And the way that we will do it is through real examples, real world examples. Okay, you will see how these examples actually are mapped into these three areas. Yes, yes. And deep learning also is helping in each of these three types. That's the relationship. So as you see here, deep learning is all over the place on these three types. So we'll start with supervised learning. So what is supervised learning? In a very simple definition, supervised learning is just a mapping from input to output. So we have some input in the real world, and we want some output, okay? And supervised learning can help in mapping between these two, from input to the output. And in supervised learning, we learn this mapping using examples, using what we call labeled examples. We are given some input values and what should be the output for these input values. Okay, and by providing these examples, we will learn a model that provides such relationship. Okay, that can help us map from any given input to the corresponding output. So we have a real world input, and we want a real world output. In between, we will use or we will train a supervised learning model. Okay, now the supervised learning model, as you will see, is just a mathematical equation, mathematical model. it might not understand the real world input in the form it is in. So we have to convert that input into a representation that the model can understand, mathematical representation. Okay, so that will be the model input. And on the other side, also the real user, the user in the real world, might not understand the output of the supervised learning model. The output of the supervised learning model might be in a specific format that has to be also converted into real world output so that the user can understand it. This is very conceptual, right? So based on that, we will see so many examples, inshallah, that will make it much more clear. Here's the first very simple example. Let's say that we want to build a model that can map from the age of a child. So we will give the age of the child, and we want to predict the height of the child. Okay, so how many inputs we have? Just one, the age of the child. And how many output? Just one, which is the height of the child. Okay, we in order to learn that model that maps between from the age to the height, we will learn a mathematical function or a mathematical equation. This equation, sorry, this equation will take the age as an input, will take the age as an input and provides the height as an output. And because this is a supervised learning model, it has to learn from labeled examples. What do we mean by labeled examples? Pairs of input and output. So as you see here in the figure, all of these orange or brown points are real examples that are labeled. Why are they labeled? Because they represent an age and corresponding height. So for example, this point, maybe it's like 1 year, and maybe this is 30 centimeters or 40 centimeters. Okay, and each point is like that. It represents a pair of input and output, an age and the corresponding height. And from all of these examples, we want to learn a general relationship so that we can apply it on any age, okay, other than the ages that maybe are in the provided labeled examples. Yes. They are, of course, real data. Yes, real data that are provided to train the model, to get specific model that can learn the mapping between the input and the output. Okay. Yes. Exactly. Okay. I have to learn from data. I cannot just write directly a code that convert from the age to the height. Okay. Why couldn't? Maybe I can think of an equation, right? I can say, مثلا, I will multiply the age by something to get the height. Okay, but that might be different from place to place, from time to time, right? From country to country. There are many factors, right? So it would be better to, much better, much easier even, to learn that relationship from given data, from given examples. Okay. So as you see here, the green curve is just like a function. Okay, just like a function that maps from age to height. Okay, and if I give you just the orange or the brown points, you can think of many functions, right? There are many functions that you can learn from these, or you can try on these points, right? So we can say generally that any learning model is a family of equations or a family of functions. The green curve here is just one of the equations. Okay, but there are many. Sorry, it is learned from the data that we observe. Yeah. Okay, so we try. The model represents a family of equations, but which equation exactly we will use, that depends on the data, the labeled data that we will use to train. When we say training or fitting the model, That means that we are searching through this family of equations to find one that is good enough. Hopefully the best. Okay, hopefully the best. Okay, is that clear? Okay. Right. Now we call this type of problems regression problem. Why is it a regression problem? Because the output is a real number, is continuous. So whenever the output is continuous, then this problem is a regression problem. But why is it supervised learning problem? Why is it supervised? Because we learn the model in a supervised way. There is supervision. Where we get that supervision? From the label data, from the data that says what is the input and what should be the output. That's the input, that should be the output. Okay. Now let's connect that to our course. In our course, we will learn a specific model of machine learning, which is called neural networks, right? So since we said that any supervised learning model or any learning model is a family of equations or family of functions, of course, also deep learning, or deep neural networks are just a very flexible family of equations. Okay, but which one we should use? We will have to fit it to the data that we have. Okay, of course, that might not be very clear now with the examples. Inshallah, would be more clear. Now, when we say fitting deep neural networks to the data, this is what we mean by deep learning. Okay, we are learning a specific deep neural network for a specific problem from specific data. Okay, so whenever we say fitting, that means training. That means finding a good model, good specific model for the problem that we are having. Okay. Right. Now we will see a sequence of examples, of real examples. This example is extending a little bit over the example that we just saw. Here we have a specification of a house, and we want to predict the price for that house. So we can give the area of the house, how many bedrooms we have, how much was it sold before, if it has a parking spot with it or not, and so on. So that's the real input, right? Now, of course, it has to be given in a specific format that the model can understand, which is usually a mathematical format, just numbers. Okay, so we'll have it as a vector of numbers. Each number represents one of the features or information that we are given in the input. Now the output is just also a number because we are talking about predicting the price of the house. So the output is just a vector of one number. Okay. Now why is that a regression problem? Because the output is no, not just because the output is a number, because the output is continuous, is a real number. Okay, because it might be 340.5, for example, right? So it's not discrete. And here the conversion from the model output to the real world output is very trivial, right? We can just say that we expect that the network will provide the number in thousands. So when we present it to the user, we just say that this is 340K or 340,000. Yes. It's a real number. It's a floating point number. Okay, it's a real number. Okay, it's not, doesn't have to be integer. It doesn't have to be discrete. So that's a regression problem, and more specifically, we call it univariate regression problem. Now, univariate because it has just one output. Okay, so univariate regression. Regression because the output is continuous, and univariate because we just have one output. Here's another, okay, and usually we use fully connected neural network to solve such problems. Here's another problem or example. We have the input here is a chemical structure or molecule structure, okay? And from that structure, we want to predict two things. We want to predict the freezing point and the boiling point, okay? So that's the real world input, and that's the real world output. Of course, again and again, we have to convert the real input into an input that the model can understand. Usually, it's just a list of numbers. Okay, regardless of how these numbers we come up with now, we will go through that inshallah in different points in the course. But we have to have a model input. Now, the output, how many outputs we have? Two outputs. So is that univariate? No. It's called, since it's more than one output, this is called multivariate or multivariate regression problem. Why is it a regression problem? Because it's continuous, right? Right? Okay, so because it's continuous, the output values are continuous. Type. If you look at the model output here, these are numbers. Usually, these are the direct values that we would use. It. So the conversion here is simpler, is similar to what we saw in the previous one. But sometimes the model output might not be simply converted to the output, okay, to the real world output, as we'll see in other examples. And for that, because the input here is a graph, we use a specific type of neural networks called graph neural networks. Okay, here's a third example. Here we are given text snippet, okay, that represents a review of a meal. So I went to a restaurant, I had a meal, and I write a review of that meal. And I want the system to predict whether this review is positive, which means that I'm happy with the meal, or negative, which means that I'm not happy with the meal. Okay? Right. Now, is that a regression problem? Why not? Yeah, because we don't have real number, right? Because we don't, the output is not continuous, right? Actually, the output is categories, right? And when the output is from different possible categories, we call this a classification problem, because we want to classify the input to be either a positive or negative. And when we have just two categories, and we call them actually classes, when we have just two classes, we call this binary classification. Okay, binary classification. Right. Let me ask you another question. How many outputs we have here? Is it two or one? Ah, it's one output. It's okay. When we talk about the output, we talk about the output that the user is getting. Okay, so the user here is getting just one value, so one output. But the fact is, this output can be of two possible values, positive or negative. And here, specifically in this example, you can see that the model output actually is two outputs. But these are usually the probabilities of the two classes. So here, in this example, the probability of being positive is 2%, and the probability of being negative is 98%. So the output or the output that the user can see is just an interpretation of this, which is probably the maximum of them. I shouldn't say to the user that the probability of the user might not understand this, but the user will understand whether this is positive or negative, right? So out of this, we can say whether it's negative or positive. Yes. If they are, and by finite you mean discrete, right? Because if they are not discrete, then this is regression. in um, if these categories, if you can call them categories and they are discrete, okay, then this is classification. There is a type of classification called ordinal classification because there is an order of the between the classes. Uh, let me give you an example. Um, like the grade, yes, A, B, C, D, E. No, there's no D here. F. A, B, C, D, F. Okay, so there is order, right? There are 5 classes, or maybe 9 if we add the plus, but they are discrete and there is order between them. So it's a classification problem, even if we represent each one by a number, by the way. It's still a classification problem, and it is ordinal. Okay, the problem itself, but you might use a regression model to help solving this and convert eventually the number that the model will provide to one of the classes. Okay. Yeah, if there are the discrete values, then it's a classification. Okay, it's not regression. The problem. Okay. No, here they are not integers, right? Positive and negative. These are. We will have other even examples that are completely not even ordinal. Okay, we'll see that. Type. Usually, when we process text nowadays, the state of the art models are called transformer networks, and inshallah um, we will study this in the course. Here's another example. I don't know, fourth or fifth. Here we have an audio snippet as a real input, real world input, and we want to see or we want to predict the type of that audio. Okay, is it jazz? Is it classical? Is it metal? And so on. Okay, type. How many outputs we have here? One. Okay, one output. Very good. So it's univariate, right? Type. Is it classification or regression? Classification, right? Because we have multiple classes. Okay, multiple discrete classes. Here, the discrete classes are not ordered, right? Yani positive and negative, maybe you can say negative before positive, some, yani, maybe, okay, or better than. But here, there's no order between them. Type. What are these numbers? Again, probably these numbers are probabilities of the classes, and out of that we pick maybe the maximum, and we provide that to the user, the name of that class to the user. Type. Why is it called multi-class? How many possible values that we can have? More than two. Yeah, if they are just two, it would be binary classification as we saw in the previous example. But here we have more than two classes, so this is multi-class classification. Okay. And usually, because this is sequential data, we use a specific type again of neural networks that is called recurrent neural networks, RNNs. Here's another one. Now we have an image, and we want to say what is this image representing. Is it apple? Is it bee? Is it bicycle? Is it clown? Is it student? Is it classroom? What is exactly in this image? What is the main object in that image? Again, this is a classification problem, right? Because we have discrete classes, discrete categories. Is it binary classification? Why not? Yeah, because that one output has multiple values, okay, multiple classes. Okay, so it's multi-class classification. Yes. Okay, so this from where you what do you mean by from where? This is the output of the model. So the model solves the problem by predicting a probability for each class. But that's not shown to the user. That's not the real world output. The real world output is just the name of the class. Okay, remember the very first slide when we say we have this one, when we say we have not this one, this one. the real world input and the real world output. Okay. Now the model doesn't have, because the model is mathematical model. Okay. It doesn't have to present its output or provide its output exactly in the format that the real user can understand. Sometimes it it does it in a different way. So in this example, it is that this one? No, this one. It estimates the probability for each class. But then the application picks the one with the maximum probability to provide to the user. And imagine that I will give the user this vector. Would that be, of course, will not be understood. Okay. So that's the conversion step. Of course. This is supervised learning, right? We are talking still with supervised learning. We said that with any supervised learning problem, we will have to have a set of labeled data. Of course, it saw before images for each of these classes. Okay. Yes. We'll talk about that later. Okay. For now, you can think of this as the RGB values for each pixel, intensities of the colors of the pixels. Okay. Okay, let's continue. So for this, because we have the input as an image, nowadays images are processed by a specific type of neural networks called convolutional neural networks. Inshallah, we will study in this course. Another example, we have an image, okay, and we want to segment the background from that image. What do we mean by segmenting the background? It's like detecting the background so that we can remove it. Okay, so in this case, the output should be whether every single pixel, the image is a rectangle of pixels, right? Every pixel, I want to see if it belongs to the background or not. So imagine this image. You see this image? Okay, I can have this output, which means the cyan color here is just the foreground or not the background, and the black is the background. Okay, type. Now, how many outputs we have here? Two outputs only? One output? Okay, two possible choices because we have background or not, right? But how many outputs? Many. Number of pixels, very good. Because we want a value for every pixel. Okay, so every pixel in the image, we want to say whether it's background or not. So it's a multivariate classification. Yeah. But for every pixel there is an output. Okay, there is a value. There is a value for every pixel. Now, so this is multivariate. Now, is it classification or regression? Classification, of course, right? Because it's categorical, right? It's either background or not. It's not continuous output. Type. Why is it binary? Yeah, because every output, okay, has two possible values: background or not. Okay, is that clear? And for that, we use a specific type of CNNs called convolutional encoder-decoder network. Is there another example called depth estimation? Here we are given an image. Okay, we are given an image, and we want to predict for every pixel in the image how far it is from the cameraman. Yeah, for example, it seems to me that this guy on the bike is very close to the cameraman, right? And the car also is very close. But this tree, I think if this is a tree, is a bit far, right? So I want to estimate for every pixel, I want to estimate the distance. That's why it's called depth estimation. Okay, right. Now, is it regression or classification, regardless of what is written on the slide? Is it regression or classification? Why? Because we are estimating continuous values. Okay, so it's a regression problem. Why is it multivariate? Because we need a value for every pixel. There are many pixels. There's not just one output. There are many outputs, more than one output. Okay, is it clear now these different types of supervised learning problems? But why are these all called supervised learning problems? Because to learn these models, now we are saying just map from the input to the output, right? That's easy to say. But to learn such models that can do this mapping, we have to have labeled data. We have to have labeled pairs of input and output. Okay, so I have to have many images like this and the depth, okay, for these pixels. But what do we see here on the slide as an output? يعني the model output, the model output itself can be just numbers, right? That represent the distance. But imagine that I give these numbers to the user. It will be very hard to understand, right? Especially this is an image, 2D image. Okay, so this is just like a presentation that is more friendly to the user. By colors. If the color, I think if it's a dark color, that means that it is close. And if it's a bright color, it means that it is far. So now we can understand. That this guy is close, this car is close, maybe this building is a bit far, and so on. Okay, so this is more friendly to the user. We use the same type of networks to do that. Okay. Now, this is a quick recap of the terms that we have discussed so far. Regression means that we have continuous numbers as output. Classification means that we have discrete classes as output. Two-class and multi-class classification treated differently. I think you saw that when we have just binary classes, we can use a different type of networks than or solutions than the models that we can use for multi-class classification. Univariate means we have just one output, and multivariate means that we have more than one output. Any questions on that? No questions? Okay, let me see if you really understand what we just covered. Okay, here is a problem. I want you to think about it first before you answer the question. Given a news article, you know what we mean by news article, right? I want to predict if it is political, sports, or economical. That's the definition of the problem. Now the question is, what type of a problem is that? Okay, think about it first. Take some time to think about it and then answer. Multivariate classification. Let's see. Let's take it step by step. Okay. First, is it regression or classification? Why? It's not continuous. It's just categories, right? Okay. Very good. Type. So we exclude the regression ones, right? Okay. Now we have the classification ones. Now, is it multivariate, binary, multi-class? Which one? How many? To say whether it's univariate or multivariate, we check the output, the number of outputs here, right? What are the number of outputs here? It's one output, but with three possible values. That doesn't mean it's three outputs. Okay, so that means that it is univariate, okay, which is not written here, I think. But at least it is not multivariate classification, right? Right. Now, is it binary or multi-class? Why is it multi-class? Binary means two. How many classes we have here? Three. Okay, so it is multi-class classification. Right. Any question about that? Is that clear? Okay. So let's continue. Now, let me show you. So we went over good number of examples, right? All of them are real examples. I will show you other real examples, but they are a bit different. I will show you 3 examples, okay? A little bit different, not a little bit, different from the examples that we saw. And then I want you to think about what is common about them, how they are actually different from the examples that we saw before. Here's the first one. Translation. We are given text in one language, which is English here, and we want to translate it to another language, which is French here. Okay? So again, we have to have the model input, which is just numbers. Don't think about how we got these numbers down from the text. We'll talk about that later. And also the model will output some numbers, and these numbers will be translated into, will be converted into text. Okay? Right. You understand this problem now? Okay? It's called machine translation, by the way, because this is automatic translation, not human made. Second example, we call it image captioning. We are given an image like that, and we want the system or the model to give us a description of that image. So that's a man on a horse holding a bird, and so on. Okay? So from image to text. The previous one was text to text. The third one is the opposite. You are given a description, okay, of an image, and you want the system to provide an image that represents that description. Whether this can actually happen in reality or not, of course, as you see here, it's very artificial. So this is called image generation from text. You are given a text, and you can and we want the system to provide the image. Okay. So back now to my question: what do these examples have in common? Okay. So what one feature that is in common between these examples, that we don't have just one possible output, one correct output. Okay, so we can generate multiple images that represent the same text. We can generate multiple descriptions for the same image. Even here in translation, we can have different translations, a little bit different, for the same input, right? So that's one thing that is different. In the previous set of examples, we didn't have that, right? Okay, one input should have specific output. What else? What else is in common that makes these 3 examples different from the previous examples? Yes. Okay, so the output is generated actually. Okay, it's not exactly determined beforehand. Okay, even in training, we might not see exactly this image in training. Okay, so the output is generated, um, which makes these problems much more complex than the problems that we saw before. Right? Okay, what else? We need lots of data, you mean, right? To in order to learn something like that, right? And in order to have a machine that can generate an image that didn't see before, it has to see so many images and learn some even rules of images, okay, from lots of data. What do you mean by rules of images here? يعني something, يعني the image has to be logical, right? Okay, and let me explain that by an extreme example. If you take, يعني we can say easily that not any random set of pixels can represent logical image or a real image or something that looks real image. Okay, or at least an image that I can understand. If you take, for example, if you take an image, if you take this image or that image, okay, and randomly permute the pixels here, and then represent it as an image again. Would you understand? Would you be able even to get the original image? Maybe not, right? So pixels here are not random. Nature is not random, right? So there are rules. There are rules, and to um, learn these rules, you have to see lots of data, lots of data. Same with text. These words are not random, right? And I cannot put just a random list of words and it will be plausible description of an image or even plausible text snippet. Okay, there are rules. We call these rules in language grammar. Yeah. There is a grammar for text. There is grammar for images, right? And these things are learned from lots of data. So mainly we capture, I think, the main common features that I have in mind here. So very complex relationship between the input and output. Sometimes maybe we have many possible valid answers, not just one, and the outputs obey rules, and sometimes even the input obey rules. So here the language obeys grammatical rules for text, for images. The natural images also have rules, and usually, and this is inshallah what we will see in the course later, we learn the grammar of these data from lots of unlabeled examples. I don't need to learn grammar from labeled data. I can just give millions of web pages or billions of web pages and books, millions of maybe thousands of books and hundreds of thousands of books and articles and so on, so that the model can learn some statistical features that can represent the grammar of the language, similar to images also. Yes. Okay. No, these are not rules. Features that are common, yeah, that make these examples a bit different from the others. No, image classification, I have already determined a set of possible output, right? So it's much easier here. Even if there are so many, I have listed them. Okay, and I have examples for each. Okay, but still, this is more challenging because you are generating something that you didn't see. Yani in classification, in regular classification, you are classifying among predefined list of categories. Okay, so whatever the output that of the system will be just one of these. It cannot be. Yeah, the system cannot say, okay, no, 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 it's a completely different category. No, it can say others maybe. If others, but in this case, others will be one of the predetermined classes. Okay, so it's different. Here we are just generating something that might not be seen. Okay, so with that, we are linking to the next type of machine learning, which is unsupervised learning. So in unsupervised learning, we learn from data without labels. So we don't have labels, but we have data. Okay, but we don't have any labels. There are many applications of that. The most famous one is clustering. But there are others like finding outliers, generating new examples, filling in missing data. We'll go through examples of these. The first example, as I told you, the most famous example is the clustering example. So given this set of images, I want to cluster them into similar images. So for example, I want to say these examples are similar. So they are in one cluster. These images are similar, so they are in another cluster. And these are similar, they are third cluster, and so on. This is unsupervised learning because we are not given any labels. We are not given any categories, by the way. Sometimes even we don't know how many clusters are in the data. So the goal in general from unsupervised learning, or the objective from in unsupervised learning, is to learn the structure of the data. Okay, some structure. Maybe learn similar things and put them together. or learn some statistical features of the data, depending on the structure and the content of the items here, which are images. Okay, there is a way uh, to predict the similarity between images. No, it doesn't need. No, by presenting by okay, so we will not talk about clustering in this course. It's in machine learning, but the idea is to find a good a good representation of the item, so that I can compute similarity between different items. Okay, okay. So the idea is to try to, here we have example images, right? So I can try to find a way, features, specific features in the image, so that I can convert any image to some features. And then I compare features of that image with features of that image. I can compute similarity between them. Okay, I know this is very superficial, so but that's the idea. We don't need to have any labeled data. But sometimes, just to complete the picture to you, we can learn similarity functions. Yani I told you that we need to get features and features, right? And then compute the similarity. How can we compute the similarity? There's a function that we use to compute the similarity. Sometimes I can I come up with a function, and sometimes also I can learn a function. When I learn a function, similarity function, this is now supervised, or kind of. There is some kind of supervision. Okay, but in general, clustering, of course, doesn't need labeled data. Okay, so under unsupervised learning, there is what we call generative model. Under unsupervised learning models, there is what we call generative models, which are now the state-of-the-art models. An example of it is what we call generative adversarial networks, GANs, and inshallah we will have time to study it. There's also within generative models, there is another subtype called probabilistic generative models. And one of them is called stable diffusion models, which inshallah I hope that we will have time to cover. But generative models now are very hot area, okay? And for the reason that I think you will see in a couple of minutes. These are all photos of cats, okay? But they are all artificial. None of them is real. They are all generated by generative models, okay? Another example of buildings, maybe touristic buildings, I don't know. So that's also automatically generated. Third example for text. This is a story, okay, and it's completely auto-generated. And you can read it, and it has a meaning. Okay? You might not even detect if it is written by a machine or by a human. So that's an output of a generative model. There's also what we call conditional synthesis. So in conditional synthesis, um, it's not that we will ask the model to generate something from scratch, but to fill in the gaps. Okay. So, for example, this image, you see the child, and there is like a robe hiding some part of the child. We might say, okay, I want to change this image so that there is no these robes. I want to remove these robes. Okay. So I will just um, point or label these regions. Okay, or any tag them somehow. Okay, it's like removing them, and then I ask the model to regenerate the image, filling in these gaps. Yani the white areas here are just gaps that I want the model to regenerate based on the remaining image, the rest of the image. That's why it's called conditional. Okay, it's called conditional here because it's conditioned on the context, the remaining part of the image. And you can see here, it's might be not 100% perfect, but it's good enough. And you see here the part on the hand, it's really good. Okay, maybe the face is not very online. It's not bad. Okay, and you might think that this is a real image. Okay, and you see that now in many tools If there is a person that you want to remove from the photo, okay, click on that person and then regenerate the photo. Okay, you like that person so much, so you want to remove it. Okay, so that's an example. Not only in images, in text. Okay, you can say, okay, this is the start of a story, complete it. So again, this is conditional, right? Conditioned on the part that I provided. I want to continue, right? I want the system to generate the remaining of, or to continue writing that story. It's not from scratch here. It's given the context, which is the beginning of the story. Does that sound familiar to you with something that we use nowadays? ChatGPT, right? ChatGPT. Okay, so ChatGPT, it takes a prompt, right? And conditioned on that prompt, it continues. Okay, it generates whatever it thinks that it's good enough to be after that prompt. Okay, it actually tries to find the most likely, the most probable word next, and then most or probable word next, and probable word next. Okay, and that's from learning from lots of data and learning statistics of the language from lots of data. So here I gave a question. I am a CS student. How can I succeed in a deep learning course? Okay, and it gave me 8 things here. Okay, that's automatically generated, conditioned on the question that I gave. Okay, now let's switch to the third type, which is reinforcement learning. Do you have any questions before we switch to the third? Okay, so you see the difference now between supervised and unsupervised? Okay, so the third one is really different from the from the other two. So in reinforcement learning, our goal is to build an agent. It's like a program or a system that will take actions in an environment, step by step. So it takes a step, okay, based on the state of the environment. So it tries to observe some environment. It's like the world to it. It doesn't have to be the real world, but specific world to it. It observes what's in the state of that world and take an action. And when it takes an action, it gets a reward. The reward might be positive, which means that this action is really good. Reward from the environment, okay, or negative, which means that maybe the action was not good. So it learns from these rewards. So it takes an action, get a reward. Okay. Sometimes it might take an action and doesn't get a reward. It has to continue. Okay. So it learns by making actions and getting back a reward. And with taking the action, it changes the state of the world, of course. Okay. Let me show you, I think, an example to understand what I mean. Of course, here we don't receive any data. We observe the data through the environment. The classical example of reinforcement learning is chess, is playing chess. I want to build an agent that plays chess. Okay, so what is the world here? The chessboard. That's the world for that agent. Okay, and the state is the position of the pieces, which pieces are still there, and the position for each piece. And what are the actions? What are the possible actions? The possible movements, right? I can move this here, I can move this here, and so on. Okay, and the agent has to take an action in its turn. One action. Type. What is the reward here? Maybe one action I will not get any reward because there is no pieces that was taken or anything. Okay, or maybe it will take a piece from the opponent, or my piece will be taken in the next. So I might get some reward or penalty. Or I can even get a reward that is very delayed. At the end of the game, I will know whether I will win or lose, right? It's very delayed reward. And that might actually rely on one specific movement that I did good or bad. And maybe I did a very bad movement, and after 20 or 30 steps, I lost the game. So I need to learn, I need to build the agent so that it can learn that this specific move, although it doesn't get the losing penalty immediately, it gets it maybe after 30 or 40 steps, but still learn that this is a bad move. Okay, so this is reinforcement learning. It's not supervised because there is no labeled data, and it's not also unsupervised because there is some observations that the agent is getting, some reward that the feedback that the agent is getting from the environment. Type, where is deep learning here? Deep learning is helping here to map the state that we are in, the input, to a specific action. So it tries to learn from given state what should be the action that I need to take. Okay. Type, yes. It's not easy to know whether this is the best or not. So that's a challenge. Ah, yes, we exactly. It the agent here tries to get the action that is most rewarding, but most rewarding on a long run. Yani it doesn't have to maximize in a short term. Okay, يعني it has to think about the future. Okay, think طبعا in some way about the long term reward rather than the short term reward. Okay, and that's why actually that's one of the difficulties in reinforcement learning. So there are many difficulties in reinforcement learning actually. One of them is that you might take some action twice, some move twice, but you get different movements from the opponent, so the reward might be different. Okay, and sometimes even the rewards are stochastic. Yani the opponent does or doesn't take your piece, so you might not get a reward actually. It's random. Also, there is the temporal credit assignment problem that we said. You might not get the reward immediately. You might get the reward in 50 or 60 or maybe 100 moves when you know that you lost or won the game. There's also the nice trade-off between exploration and exploitation. Should the agent use what it learned already before, or it should explore new actions? This is something like when we think about going to a restaurant. Should we go to the restaurant that we used to go and like, or we should explore new ones? Maybe they will be better than the ones that we saw before. Okay? So that's the exploration is to discover new things. Exploitation is to use what you know already. Okay, which one we should do? So that's a trade-off, and that makes reinforcement learning really challenging. Okay. Okay, finally, I just list here. So that was really very brief introduction to reinforcement learning. I hope that inshallah we will have time at the end. I'm not very sure, but it's the last thing that we might learn in this course. And actually nowadays it's complete courses. And there's a complete course about not here, but in other universities there are complete courses on reinforcement learning only, and deep reinforcement learning in particular. We can use deep learning to do reinforcement learning. I will close by talking a little bit about history in machine or deep learning. Here's a very short, very quick timeline of the landmarks in the history of machine and deep learning. You will find that there are, if you look at the times, the year of each landmark, you will find that there are four phases in time, or four stages in time. The first one is when we start to do something called neural networks around 1960s with what we call perceptron. This is the simplest neural model. We'll talk about it inshallah. And that was not very useful. But then in 1980s and 1990s, we started to know how to train larger networks with the backpropagation algorithm, but still it was not at scale. It was still very limited and small networks. The breakthrough happened in the last 10 years or 15 years when we started to know how to do the training at scale and how we can train deep networks, very large networks with billions of parameters. And we had in these 10 years many breakthroughs in solving many problems. But then another breakthrough happened in 2022 with moving that from research labs to the user. Okay, and we all saw that happening when we use ChatGPT. Now these kind of models can be used easily by humans, by users. Okay, so ChatGPT and its family, like GPT-4 and the others. So these are four different stages in the history of machine and deep learning. Nobel Prizes, right? They are in specific fields. Unfortunately, there is no one in computer science, but there is another one that is very similar to Nobel Prize called Turing Award. Okay, it's also given every year, and in 2018, it was given to these three pioneer researchers that are actually considered the fathers of deep learning. Benju, Hinton, and Deacon. They are they made or they were behind big advancements in deep learning in particular. So they got this prestigious award in 2018 together for their work. Okay, so where are we going from here? So that concludes the introduction. Okay, so now we have covered chapter 1 from the textbook. I was actually planning to cover also chapter 2 today, but I don't think we have time now. Inshallah, next lecture we will talk in a bit more detail about supervised learning. We will take one example and show all the aspect of machine learning in general on that example. And then from the lecture after, which I think will be inshallah on Wednesday, we'll start talking about neural networks. So we'll start with shallow neural networks, then deep neural networks. Then we talk about how we can train, how we can guide the training of neural networks, and how we can actually train a network, and how we measure the performance of a network. That will be up to, I think, chapter 9 in the next 5 or 6 weeks, inshallah.